another week.
Mhm.
I think it's time that we talk about a couple of topics that are sort of nicely lumped together. We want to talk
Mhm.
about some of the brightest objects in the universe.
Mhm.
So these are quasars. These are, these supermassive black holes accreting lots of matter, etc.
Mhm.
We can see them right across the universe, and everybody loves a quasar.
Mhm.
But I know you did your PhD in this, so I'm sure you're going to talk about it.
Oh,
Um, yeah, so quasars, of course, they are also powerful probes. I hate the word probe, but they basically reveal a lot about what is between us and them in the universe. So
Mhm.
when you look at the light that's traveled across the universe from a quasar, it gets imprinted with a signature, and that signature tells us something about the universe. So why don't you tell people a little bit of background about this thing called the Lyman alpha forest?
The Lyman alpha forest. Yeah, one of my favorite things. Everyone who's got a PhD is just dying for it to somehow come up in conversation. So if it has to come up like this, then that'll do. So as you said, we've got these things called quasars. We can see them at enormous distances, and the great thing about that is, again, what they show along the line of sight. Usually, if you want to see something out there in the universe, it has to be really bright. You need, a trillion stars to fire up in a little region, and then you see a galaxy, a little region. Um, so what the Lyman alpha forest allows us to do is a bit like you said. It's seeing bits of the universe, but in silhouette. Is one way of thinking about it. It's not quite a perfect analogy, but it's not bad. So imagine it's a moonlit night, and ordinarily you wouldn't be able to see the black cat that's moving across your fence. But if it walks in front of the moon, suddenly you can see its shadow, and then you can see the cat. So one of the keys here is the Lyman alpha in the Lyman alpha forest. So what this refers to is an interesting fact about all atoms, and especially in this case about hydrogen. So if we have our little picture of an atom with the nucleus at the center and the electrons going around the outside, when we describe that using quantum mechanics, we find that the electron is allowed to orbit in certain specific orbits and not just wherever it likes. And so if it wants to change its orbit, it can't just smoothly deform its orbit into another orbit. It's got to jump between them. And in that jump, there's a difference in energy, and that energy will be either needs to be supplied by or will be released as a photon of light. So here's our, let's have a hydrogen atom here, which is just a proton, and there's an electron going around the outside, and let's put it in its lowest energy state where it just likes to hang out. Okay, if I put in a particle of light at exactly the right frequency, the right energy in that light particle, I can make that electron jump up to the next level from level number 1 to level number 2. And once it's up at level number 2, there's some probability that in a certain amount of time, actually pretty quickly, it'll jump back to level 1 where it kind of wants to be, and it will release a photon with the same amount of energy.
So can I ask a silly question here?
Hit it.
So are you telling me that the universe is full of hydrogen atoms sitting in their lowest energy level, waiting to jump to between one level and the other? Is that the sort of normal state of hydrogen in the universe?
For the most part, except, there's always an except. That's if the hydrogen nucleus, that proton, has an electron around it. There's a certain amount of energy you can put in, which is a bit more than just to jump from 1 to 2, where it completely jumps free. You can just knock an electron off the proton entirely, and then you just have a free electron and a free proton. That's called ionized.
Ionized, yes, that's the word.
Good. You can do that with any atom as long if it's got an electron. There's the number of electrons that it needs around it in order to be electrically neutral, so to have the same charge in electrons as protons. That's the neutral atom. And then if you throw light at it hard enough, or you smash it into something hard enough, or whatever, you can start knocking those electrons off, and then you get ionized, ions, basically, ionized versions of those atoms. As well as that, you can, of course, start putting hydrogen into molecules with other hydrogen or with something else and make water and all those sorts of chemistry things. But basically, hydrogen is the most abundant element in the universe. So it was thought some of it's got to be out there neutral somewhere, right? I mean, we do see evidence of it in our galaxy. There's a way to see it directly from in radio waves, which we can discuss in a bit more detail. And so the thought is as follows. Okay, I've got a quasar over there, miles and miles and miles away, lots of miles away because it's space and all that. And it's going to send a whole bunch of light towards me because quasars have a very broad spectrum of light that they send out. When they send out photons, they send out photons with lots of different amounts of energy. And some of those are going to have just that right amount of energy to interact with a hydrogen atom. So a good way to think about this is there's something called the cross section. And all that is if I have a nucleus here and a hydrogen atom here, and then I throw a light particle at it. And how big does the atom look to the light particle? So imagine it's the bullseye of the dartboard. How big is the bullseye? How hard is it for me to throw it just right so that the light interacts with the atom? And that depends on how much energy there is in that particle of light. And if you get the amount of energy that equals one of these jumps, say from 1 to 2, right, from the ground level up to the first excited state, suddenly that hydrogen atom looks really big. That's a nice big target. It knows what to do with that photon with that amount of energy in a bit of light. And so it wants to interact with that, if you want to put it that way. And so now it looks like a really big target.
As an aside, I'm not sure if in Lyman alpha forest land it's the same, but in particle physics, of course, the cross-sectional area that has units of barns, right?
Yes.
And but it doesn't have the E like you.
No.
And I've always wondered if the source of that is something along the lines of trying to hit the side of a barn.
Oh, that would be great.
Yeah, but we should check that one.
So the Lyman alpha in Lyman alpha forest refers to the gap between the ground state and the first excited state. Okay. So if you have light with exactly that frequency, that's called a Lyman alpha photon. Now, if you go from the ground state, not to the first state, but to the second state, then we go Lyman beta, and then we go through the Greek alphabet. And if instead of starting at the ground state, you start at the first excited state, and then you jump up to the higher ones, there's a whole lot of different series of light that you can get out of hydrogen. One of the reasons astronomers love this is because it's a signature in the light that we see. If you see that specific wavelength, you're seeing hydrogen, which is, there's no way you could get out there and, work that out any other way. Well, there's very few ways you could work that out any other way.
Okay, so that explains the Lyman alpha part. Forest.
So as we left our story, there was a whole bunch of photons, whole bunch of particles of light heading towards us. And the ones that have the amount of energy that's this Lyman alpha amount of energy, when they start going out into the universe, they see hydrogen atoms as being really big targets. So ordinarily when light travels around through air, the air presents a target for the light we see around us, but it's a very small target. And so light can travel a long way through the atmosphere without being affected. It takes about 100 kilometers of travel through the atmosphere before you actually notice like a haze starts to descend. So you can imagine the light's heading along, and then if it hits a particle and heads off in a random direction, I was trying to see that thing over there, but now some of the light went missing, and so I can't see it as well. And other light gets scattered in to my line of sight, and so we see a sort of a mist. So what that means is, all right, here's all these photons. They're all heading out through the universe, and the ones that are bang on the Lyman alpha wavelength, they see a fog, and so they barely go anywhere, right? As all these photons start streaming towards Earth, those specific ones, and it's 121.6 nanometers. That's how you know I did my PhD in this, when you have a number like that memorized. It's those specific ones, they hit a patch of neutral hydrogen, and they just take a random right angle turn, or just turn some random direction, just head off somewhere else. So they're no longer heading towards us on Earth, almost certainly. There's some tiny chance they might actually end up going in the same direction. But basically, like in a fog, they're gone. The forest bit comes because not only are those particles of light heading out towards us, the universe is expanding as they come towards us. So all of those particles of light we can think of, and this is one of your bugbears, we can think of them as being stretched by the expansion of the universe. That's a useful way of thinking about that, although you don't like it very much.
So, but I think you might need to clarify something. So the light that comes from the quasars, isn't at a single wavelength.
No. So at the center of a quasar, we've got matter falling into a black hole, swirling around in an accretion disk, heated up to ridiculously high temperatures. All sorts of crazy stuff is going on. And so all sorts of light is coming out of a quasar. We see quasars at radio wavelengths with very long wavelengths. We see them in X-rays with very, 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 very short wavelengths. And the Lyman alpha photons, those are in the UV. So I mentioned 121.6 nanometers. Visible light is on that scale 300 to about 800. So we're at about a third-ish of the wavelength of blue light. So we're in the UV. But all of that stuff comes out. A whole bunch of stuff comes out of quasars. This is why they're so wonderful to look at. And so imagine the scenario. Okay, we've got our horde of photons. Let's put them all in a box and send that box towards Earth. Okay, the ones that leave the quasar with exactly that Lyman alpha frequency, right, the box heads into the first patch of neutral hydrogen it finds, and those all leave the box. They're gone. They take a right angle turn. They're finished. Okay, but the rest of them, they're fine. They keep going. But as we go along in the universe, every photon in the box gets a little bit stretched. And so later on, we hit another patch of neutral hydrogen in the universe, more of these things to interact with. And now some of the photons, which were fine when we went through that last patch, they weren't at the Lyman alpha frequency. Now that they were a bit shorter than the Lyman alpha frequency, so that they went through it fine. Now they've stretched to have just that right frequency, just the right amount of energy to now interact with neutral hydrogen. And so at the time when those particles of light hit this next patch after being stretched a bit, they take a break, they take a right angle turn, and they're gone from the box as well. And so there's, for all of those photons, which are just a bit shorter than the wavelength of the Lyman alpha photons, right? They're going to get stretched, and they've got a date with destiny. The box is going to head out across the universe. At some point out there, it's going to be their time. The stretching of the universe is going to have stretched them into the Lyman alpha, amount of energy, the Lyman alpha wavelength. And if at that time the box goes through a cloud of neutral hydrogen, they will be kicked out. But if it doesn't go through a cloud of neutral hydrogen, if it just goes through an empty bit of space, or ionized hydrogen, which doesn't, there's no electron there, it's not going to interact via the Lyman alpha frequency. If they go through that, then they'll survive. They won't see neutral hydrogen. They won't hit that stuff. And so they won't take the right angle turn. So they will arrive at us. So we are at Earth. The box arrives. Right? We open it up. We have a look at all the photons via, actual scientists doing things with telescopes and all that sort of stuff. And then we can sort of have a look at what wavelengths of light made it to us. We can have a look at all the rest of the wavelengths of light to work out how far away the quasar was, because we can tell how much all those other ones are redshifted. But when we go and look at the Lyman alpha frequency and the ones that would have left the quasar with a slightly shorter frequency, shorter wavelength than that, if we look at all of those, we can map those to a certain place in the universe. We can say, okay, all the ones with this particular wavelength are missing. They would have been in the Lyman alpha range when they were this far away from the quasar. So there must have been a patch of neutral hydrogen there. And then you look back, okay, all of these ones with this wavelength, those are here. They arrived to us. They would have been in the Lyman alpha wavelength when they were this far away from the quasar. So there must not have been a patch of neutral hydrogen there so that they could get through to us. And in doing that, we have a map, a one-dimensional map.
Okay, so what you're telling me is that this neutral hydrogen gas is not just smoothly distributed through the universe, because that would just give you sort of like, that would eat all, there'd be a just general eating of the photons, is only very specific locations. So the neutral hydrogen gas is clumpy.
Right.
Why is it clumpy?
Well, so what they expected to see was something called the Gunn-Peterson trough. What you said, it'll eat them all. So we'll go and open the box and there'll be nothing, there'll be no Lyman alpha photons and none of the slightly shorter ones as well, because they all got redshifted and then eaten. Eaten's not about, that's a good way to put it. But what we see, and it's really beautiful, as we look out into the universe, we see in the local universe, we see that most of the photons didn't get eaten. Most of them got through to us. So if we look at a local quasar, we see a couple of little bumps, little chunks out of the universe, out of the forest, but most of them got through. And what that's telling us is one of two things, and we bring other information to try and work out which one of these it is, but it's telling us one of two things. Either all of the neutral hydrogen is contained in very small clumps. It's all clumped together. And so for most of the paths through the universe, you just miss the clumps. So there's instead of being a smoothly distributed cloud of neutral hydrogen everywhere, there's like a clump here and a clump there. And then for some quasars, they just get through the middle, or however you want to do that. The other thing is maybe there is still hydrogen everywhere, but it's been ionized. All the electrons have been knocked off. And there's a culprit. Okay. The culprits for that around are going to be stars and quasars themselves. They're pumping enough high energy photons into the universe that all of the hydrogen, especially the stuff outside of galaxies, is just sitting there as empty protons. And the answer, we think, from the Lyman alpha forest is basically a bit of both of those things. The universe, as it goes on, is getting more clumpy. But what that means is, the further away we look at a quasar, the more bytes there are taken out of its spectrum, the denser the forest, because the hydrogen is more spread out, and so you're more likely to hit a bit of it, and it's more likely to be neutral, not ionized. It's more likely to have the electron there going around, ready to interact with that photon coming through. So the cool thing here is as you look, and I'll show here a procession of the Lyman alpha photons as we go further and further away with these quasars, we see just, in the local, we just see a few little bytes taken out, and then some more bytes, and then some big bytes, and then finally at very high redshifts, where we're talking sort of 6, so the whole light got stretched by those sorts of factors on its way here. You basically do see the Gunn-Peterson trough. Everything got eaten. It's all gone.
So what do we learn? What is it that about the universe that the Lyman alpha forest is telling us? Why is there neutral hydrogen in clumps? What's it revealed?
So what we're seeing here is galaxy formation. What we're seeing here is gravity pulling things together. So the further away we look in the universe, and especially all the way back to the cosmic microwave background, we see a very smooth universe, and the universe today is very lumpy. And so in between, those lumps are growing. And we can see that being laid out in the Lyman alpha forest. And the beautiful thing is, we're not just looking at the brightest bits of the universe where stars have fired up. We're not just seeing the stuff that, is waving wildly from across the universe really brightly. We're able here to see the stuff that's in between the galaxies, the stuff that's slowly emptying out as it falls into galaxies. So it's a really, really beautiful way of just seeing that structure forming as we go onwards through the universe, and seeing it in the bits of the universe that are where where the last leftover, not part of a galaxy, parts of matter are left.
Okay, that's pretty cool. So we're seeing all this as silhouettes against the universe. We're seeing galaxy formation, like the dark side of galaxy formation. That's not dark matter; it's just matter that's not obviously there.
Yeah.
So let's finish up on a couple of things. So there is a phrase I've heard with the Lyman alpha forest, which I think needs a bit of explanation: the proximity effect.
Oh, yes.
Yeah. So how do you explain that? My understanding is the proximity effect is you can actually make the Lyman alpha forest vanish. How do you do that? What happens?
So here's our box. Remember the box we sent out in the universe? Anytime it hits a bit of the universe where all the hydrogen has been ionized, it gets through for free. Those photons get a free pass on their way through. One of the places in the universe where where hydrogen is likely to be ionized is right next to quasars, including the quasar that it came from. So actually the box, the Lyman alpha photons in the box, just as it leaves, those will probably get a free pass out because the quasar itself will have ionized a sort of blast radius around it. So the first part of the journey of the box towards us is probably almost certainly through ionized gas. And so the Lyman alpha photons arrive from that region to us. And we see this effect when we look right next to the Lyman alpha line at the quasar, that we do in fact see that the photons right next to that, in the proximity of the quasar itself, do get that free ride towards us.
Okay, so if I've got this right, so you're the observer, I'm a quasar. Okay, so there's a line of sight from me to you, and there's gas clouds along the line of sight. Near me, I've ionized the gas, so I don't see Lyman alpha lines close to me. What if I put another quasar halfway, not far away from the line of sight between us? What does that do?
Well, this is the interesting thing. So as well as the Lyman alpha forest, if a really, really big bite gets taken out of the spectrum, we call that a damped Lyman alpha system. It's exactly the same idea. It's just a really big bite. And when that happens, we think that that's because of it's gone through basically a galaxy. So if someone saw a quasar through the Milky Way, they would see a really big bite taken out. But anything that changes the amount of neutral hydrogen there, like, oh, there's a galaxy there, or anything along the line of sight that would ionize a whole bunch of stuff, like your quasar near the line of sight, that will affect how much light gets through. And we've been thinking about this in the gloriously named Project Tnetennba, which I will allow you to explain. But I'll explain the project, you'll explain the name. The idea is, okay, I've got the Lyman alpha forest, and I'm looking at a particular quasar watching the forest, okay? But quasars, there's another quasar near to the line of sight there, right next to it. So here's I've got to try and set this up. So here's the quasar we're looking at. And then along the line of sight, there's another quasar quite next to it. Okay. But the thing about quasars is they're not perfectly stable. They flicker, they get brighter and dimmer, sometimes on very short timescales. So if suddenly this quasar along the line of sight nearby suddenly had a bit of an episode, had a big day, ate a whole bunch of stuff, started putting out a whole lot more ionizing radiation. If there was a cloud of neutral hydrogen over here, which we see in the Lyman alpha forest, it might suddenly ionize it. And so what we could look for is, and it takes a bit of geometry to get this right, for everything to arrive at us at the right time, we might be able to see a quasar get brighter at the same time as on a nearby line of sight, suddenly a bit of the Lyman alpha forest disappears. So this one, we see this get brighter, and not only does that send more light to us, it sends more light into this cloud over here, Now, this is something we've thought through a whole bunch, and we're trying to work out if this is actually feasible to see. All
Yeah.
the pieces are there. One of the things that's hard is the best way for us to do this is if we could just pop out into the universe and just rearrange some stuff to get everything in the right place, and then it would all work out nicely. We have to sort of put up with whatever nature gives us, unfortunately. So we'd have to find the right pair of quasars to do that. But that would be really, really great to see.
Yeah.
Why is it called Project Tnetennba?
Project Tnetennba. I will leave that for the listeners to Google about where the word Tnetennba comes from.
I'll spell it for them in the comments, in
Yes.
the description below. Very nice.
But it is a piece of work that we really should finish up and write up at some point.
Yeah, apart from all the other stuff we're doing. There's one last little thing, which one of my favorite things about the forest, which we talked about in the book, available for Christmas and all good places they sell books. Suppose there's I see my map of the universe, and I see that there's a patch of neutral hydrogen out there, and I can see a whole bunch of neutral hydrogen. What I could also do is just get a normal telescope and just look in the same direction and see if I could see galaxies at the same place. Now, that's a bit hard to do because there's a really bright, quasar trying to blind us. But we could look for statistical correlations between, is there more neutral hydrogen? If there's more neutral hydrogen in a certain place, are there more galaxies around it? Because that's kind of what we'd expect if these two processes are linked. And actually, thanks to some work, I mean, it's there in the book, this is in fact what we do see, where we see a change to the amount of Lyman alpha absorption at a certain place. There's a correlation with how many galaxies we find around that place in the universe. And so this is a very nice sort of illustration that these two things are fitting together. This picture of redshift we get from galaxy redshift and from quasar absorption lines in Lyman alpha forest, that whole picture fits together quite nicely.
Modern cosmology is incredible.